Alrighty, 11.6. Today we're going to talk about surfaces in three-dimensional space. So this is kind of an extension of planes, really. Um, so generally, in two dimensions, what you're used to, what you learned before when you just graphed in the XY plane, those graphs were called curves. In three dimensions, though, the graphs that we make are called surfaces. And it's because they would be surfaces. Like if they were real life objects, they would be things that you could put something down on, or an ant could crawl on it, or a cat or a snake. I don't, yeah, anyway. Um, so these graphs in three dimensions are called surfaces, and a lot of them kind of relate to what you would expect in two dimensions. Here's a prime example. So first thing, draw a graph for the relation x squared plus y squared equals 1 in the xy plane. So if you remember from high school math, x squared plus y squared equals 1 gives me a circle with a radius of 1, centered at the origin 0, 0. So drawing that out, we have our x-axis, we have our y-axis. We go out 1 unit on every axis. In every direction, we get a circle. Cool. That's the graph for that relation. Now we want to draw the same relation in three-dimensional space. And one thing I want you to pay attention to here is how I'm going to label these axes. All right, so your textbook typically goes with the x-axis being this direction. This is the positive x-axis. And the positive y-axis this direction, positive z-axis this direction. So this is how I'm going to draw the graphs here. Generally, it's a good idea to pay attention to which axis is x and which one is y, right? Because depending on where you go, where you look, you might see different labels used by different sources. Or even if you're looking at the same problem from the same textbook, they might try to trick you, mean. But X, Y, Z, always look at how these are labeled. So one thing to note here is that this equation that we've written out, x squared plus y squared equals 1, does not involve z at all. That means that no matter what value of z I take on, the graph is going to look like this. So what we drew over here in the xy plane would essentially be represented by this circle in the xy plane. All right, so it's kind of like we're looking straight down at the ground here. Now we backed away and we see that the circle is just drawn on the floor, right? Because this equation, this relation does not depend on z, essentially we're going to have the same shape all up and down the z-axis, meaning no matter what value of z I take on, I'm always going to have a circle with a radius of 1 centered at 0, 0, whatever the z coordinate is. Right? And if I were to draw infinitely many of these, essentially, I would get a cylinder. Yep, that's a cylinder. And it goes all the way up the z-axis, all the way down the z-axis. So an infinitely long cylinder. And that's the idea, is that when we get equations that look like things we're used to in the xy plane, and they don't depend on one of the three variables, it kind of just extends infinitely in both directions along or parallel to the axis of the variable that's left out. Let's look at another example. So here we have the graph y equals x squared. We want to draw it in 2 dimensions first and then expand to 3 dimensions. So if I'm in the xy plane, we know that y equals x squared is the parent graph for quadratics. So we know that this is going to end up giving us a parabola. That looks like this. All right, cool. Easy peasy. But if we try to extend this into three dimensions, in mind we've got the x here, we've got the y here, we've got the z here. Okay. If I start off by just graphing this two-dimensional shape on the floor, right? Keep in mind positive x, positive y. So our parabola would look something like this if I were to just draw it on the floor. Because this relation does not depend on z, we know that we're going to have similar parabola shapes going all up and down the z-axis. So I could draw a bunch of parabolas all up and down the z-axis. And essentially, what this is going to result in is this, it almost looks like a sheet of paper that's been folded into a parabola. I think it kind of looks like a taco. Do love me some tacos. But the actual word for this would be what we call a parabolic cylinder. Yep. Still kind of the cylinder idea because we're essentially graphing something that doesn't depend on one of the three variables, right? All of those turn out to be cylinders of some sort. Parabolic because the floor image, right? The two-dimensional version of this is a parabola. So we end up with our little taco shell, also known as a parabolic cylinder. And that's what we get for that one. Keep in mind, this does extend all the way up the z-axis, all the way down the z-axis, and this parabola also extends all the way out. It's like an infinitely big taco shell. Okay, now for the next example, we have two different surfaces that we're drawing, both of which are going to be sketched in three dimensions. So first off, we have for part A, we have z equals y squared. Well, that looks like a parabola, right? That's really similar to y equals x squared. The only difference is um, the parabola that we draw here would actually be in the yz plane. So we think about that. This is our z, this is our x, and this is our y. Okay. So if you compare this equation, y equals x squared, to this equation, y is basically like the x. Z is basically like the y. So if I draw this parabola out, the original two-dimensional shape will be in the yz plane. So it's kind of like a parabola that's drawn on the wall this time. And we know that extends up. Because this does not depend on x at all, we know that we're basically going to have a bunch of parabolas going all the way up and down the x-axis, right? All of their vertices are going to be on the x-axis and they'll extend up just like these do, right? So if I were to just finish drawing out the tops of these, finish drawing out the parabolic part, right? Make sure I have my boundary right there on the x-axis, right? This is what I end up getting for part A. All right, so that's like a taco shell or a parabolic cylinder going along the x-axis. You're a lot less likely to spill the contents of your taco when it's graphed like this, as opposed to this, by the way. But yeah, so that's the surface for this one. So we treated it pretty much exactly like y equals x squared, right? But we just have to keep in mind which axis is acting like which one. So now let's look at part B. So this was part A, part B. All right, so again, this will be a three-dimensional graph. We've got our Z, we've got our X, and we've got our Y. Okay. So for this one, we're doing a sinusoidal function, specifically one period of the graph for sine of X. So if you think back to Y equals sine of X, right, that would be kind of like if I were graphing just this part of the sine wave, right, from 0 to 2 pi. So the x-axis is still functioning as the x-axis. The z-axis this time is functioning as the y-axis. So if you think about it, this is our x, 0. This could be pi over 2. This could be pi, 3 pi over 2, and 2 pi. So if I draw my sine wave, I know that sine of pi over 2 is 1. I know that sine of pi is 0. Sine of 3 pi over 2 is -1. Sine of 2 pi is also 0. So if I draw my initial, what we're going to end up referring to as trace, make that look a little more curvy there. There will be no pointy sine waves. Yeah. All right, we have our initial drawing, right? So this is our sine wave just drawn on the xz plane. Since this doesn't involve y at all, we know that essentially if I move up and down the y-axis, I'm going to have a bunch of sine waves. So I could essentially expand the tops of the wave, the middle of the wave, the bottom of the wave, the end, all the way out. And I would end up getting a little sheet that looks like this, right? And then we're coming over the top, down to the bottom. That's the bottom. Right, and essentially we just have a bunch of sine waves over and over again for different values of the y-axis, right? So this almost looks like a sheet blowing in the wind if you've ever had to hang dry your laundry or like rolling with the homies. Anyway, aging myself there. All right, but that's what our graph looks like. So the idea with all of these surfaces is that if you know what the graph looks like on the xy plane, you can relate to whichever variables are present and kind of just extend it in the direction of the variable that's not there. So now there's a try it, right? So what I want you all to do, pause the video and try and graph y equals z to the third. Pause it. All right. So starting off, I'm going to just, for reference, draw what the graph of y equals x cubed looks like. So we know that this is the parent function for cubics. I know that we go up that way, we come down this way. So it's not quite a line, it's kind of wavy-ish, right? But this is what the graph y equals x cubed looks like. Okay, so in this scenario that we're going to draw, the y-axis is still the y-axis. The z-axis is acting like the x-axis. So drawing out my coordinate system, got our x, our y, and our z. So the y-axis, remember this is your positive y-axis, this is your positive z-axis. So this part of the graph in the xy plane is going to go this direction. All right, and then negative y-axis goes this way. Negative z-axis goes down below. And for fun, that's the negative x-axis. Okay, so then this part of the cubic graph is going to go this direction. Oh, whoops, that's x. All right, so imagine this is our wall. The YZ plane is our wall. X is kind of just skewering through the origin point there. Since this doesn't involve X, remember, we can basically just draw this same graph on all the different values of X that we get, right? And that might be a way that kind of helps you visualize what these look like. I know that it's going to end up looking kind of like a sheet again that takes on a very specific form. So we end up with this cubic sheet. Goes off in all directions. It's kind of hard to see in this one, but but it's basically like if you were to take a sheet of paper like this, and kind of lay it along that curve. Okay. So those are all examples of cylinders, right? This would be a cubic cylinder. This would be a sinusoidal cylinder. Try saying that 5 times fast. All right, that's only one kind of class of surfaces that we encounter in 3 dimensions. Another class is what are called quadric surfaces. These are kind of like the 3D equivalent to when you learned conic sections in pre-calculus and probably saw them here and there sprinkled out in Cal 1, Cal 2. But quadric surfaces can vary a lot. Like with conics, I think you guys learned 4 of them, right? The circle, the ellipse, which in quadric surfaces, we only kind of see that as one. Then you had hyperbolas. Remember, that's like this thing. Yeah, this thing. And you had parabolas, right? And we have similar equivalents to all of those things with quadric surfaces, but there are 6 major types that we are going to look at. So first thing I'm going to say, do not get intimidated by this. Very seldom will you actually see something that looks anything like that. Typically, when we're trying to classify quadric surfaces, we have our equation written in factored form. It looks a lot cleaner than this. I mean, think about it. Back in pre-cal, you would get problems where you have an expanded equation like that, and you'd have to complete the square and write an equation for whatever type it was, right? So on the next sheet, we have this nice little table that I made that kind of goes through what the different ones are, what all our different quadric surfaces are. And it gives you some information about them. Like, what does the equation look like? What can I see in this equation that tells me that it's this kind of quadric surface? And then we have some information about the traces. So traces, we mean, actually, I'll point them out when I draw the pictures. Okay, so first up, we have what's called an ellipsoid. So this one, think about like an ellipse that's like an oval shape if you were to spin it around and around to make a 3 dimensional object. Right, that would be called an ellipsoid. And in this case, A, B, and C are all constants. Actually, in all these cases, A, B, and C are just constants. And there are 2 things we want to look at. One, positives and negatives for all of my squared terms. 2, is the right-hand side 0 or 1? So for an ellipsoid, all 3 squared terms are the same sign, right? Positive or negative. The right-hand side of the equation is 1, and then A, B, and C kind of tell us the relative radii in each direction. Like we would have a radius of A along the x-axis, a radius of B along the y-axis, and a radius of C along the z-axis. So this kind of goes to our idea of what these traces are going to look like. So if I were to draw this, we've got our x, we've got our y, we've got our z. So I can basically draw three different ellipses to kind of give me the shape of this, right? Those three ellipses that I draw are going to be the traces. So if I were to ignore the z term, right, I would have x squared plus y, x squared over a squared plus y squared over b squared. That would give me an ellipse that's in the xy plane, right? So if I had a radius of a in the x direction, a radius of b in the y direction, that ellipse would look something like this. Okay. Now, if I were to cover up the y, right, in the xz plane, I would have a radius in the x direction of A and a radius in the z direction of C. So let's say this is C. That ellipse would look something like this. Go down, intersect with this ellipse over here. All right. And then finally, if I were to cover up the x term, I would get y squared over b squared plus z squared over c squared. So that would give me an ellipse with a radius of b in the y direction, a radius of c in the z direction. So that's going to intersect at the top and at the bottom and on these sides. So essentially we get this three-dimensional shape, right? It kind of looks like a foosball, a football, but with the edges a little rounded, or like a pill, or the body of a minion, whatever you want it to be. Yeah, that's an ellipsoid. For hyperboloids, we can think of that as another class. Oh, other side note, almost completely skipped my mind. If A, B, and C are all the same non-zero number, then this ellipsoid will actually be a sphere. Kind of like how if you have a regular ellipse and the A and the B are the same, you get a circle, right? It's the same idea. So with hyperboloids, there are two different kinds. And here's kind of what you can look at to figure out which kind it is. So hyperboloid of one sheet, hyperboloid of two sheets. So hyperboloid of one sheet will only have one term that's negative, right? In this case, that's the z. And essentially, when this happens, let's draw our picture where z-axis, x, and y. Yep. All right. If we look at our traces for this one, we have an ellipse that's parallel to the xy plane. So notice whichever ones are positive, that's the plane that's going to have the ellipse in it. So xy plane, we have an ellipse where the x radius is a and the y radius is b. So again, we're just going to draw an ellipse, a little oval shape on the floor. Notice this is going to go to x equals negative a and y equals negative b. Okay, so that's one of our traces. The other trace, we have hyperbolas that are parallel to all the other planes, meaning if I look at the xz plane, I'm going to have a hyperbola. Remember, the hyperbola is the thing that kind of looks like backwards parentheses. All right, so it's going to look something like this in my xz plane. And in my YZ plane, we're going to look like this. All right. And then notice that this is going to end up making the exact same ellipse that we drew down here. So basically, a hyperboloid of one sheet kind of looks like this shape here. I like to think of it as a lampshade or the top part of a top hat. Cat in the hat. But yeah, so that's what a hyperboloid of one sheet looks like. And the way we can tell, so first off, hyperboloids are going to be are going to have a right side equal to 1, and you're basically going to have not all of the signs being the same. So some of the terms are positive, some of the terms are negative, right? With an ellipsoid, right side was equal to 1, but all of the squared terms had the same sign. They were all positive. Now, if I go on to a hyperboloid of two sheets, we have two negative terms. So two squared terms that are negative, and we're still equal to 1. So all hyperboloids were equal to 1, all right? And the number of negative terms you have is the number of sheets. Okay, so here's what this is going to look like. We'll have an ellipse that's parallel to the XY plane. For this example, we use the XY plane because X and Y are the variables that are negative. So if I draw this out, all right, we're going to have ellipses that are parallel to the XY plane, but they're not actually going to be in the XY plane, right? Then we're going to have a hyperbola that's parallel to the other planes. So it's going to end up looking like this. So we have a little ellipse, slightly bigger ellipse, slightly bigger ellipse, slightly bigger ellipse. It's basically making like this bowl shape. And you can see how one of your traces is going to be a hyperbola because you're going to have one up here, and then you're going to have one down here. All right, so essentially, a hyperboloid of two sheets is going to look something like that. I like to think of it as two people wearing ghost costumes on Halloween in the topsy-turvy room. I don't know how they would do that. But yeah, so that's what a hyperboloid of two sheets looks like. For an elliptic cone, it looks a lot like a hyperboloid of one sheet. The only difference is that on the right side we're equal to 0. And basically what's going to happen is it's going to look a lot like this guy. Just if, we put a corset on it and tightened it all the way so that its midsection was literally just the origin. Here's what I mean. Whoops, that's X. Okay. So we have ellipses going all the way down to that origin, getting smaller and smaller. And then we have another one at the bottom. And that's basically our elliptic cone. It's like a cone on top of another cone, like an hourglass. Like sends through the hourglass. So are the elliptic cones. All right, now moving on to the last type of quadric surface, we have paraboloids. Okay, and with paraboloids, the big signal that you have a paraboloid is that only two of the three variables are squared, right? And the variable that's not squared is going to give you the axis for that paraboloid, right? So everything that we've looked at here is kind of moving along the z-axis because of how the equations have been written, right? So like with hyperboloid, with one sheet, the axis was z because that's the negative one. With hyperboloid of two sheets, the axis was z because that was the positive one. With the cone, z because that was the negative one, right? So similar idea here, since z is the non-squared term when we draw these out, the paraboloids are going to be going along the z-axis, right? But you have to keep in mind that that can change, right? The orientation of these could be different depending on which terms are negative or positive or not squared, right? So keep that in mind as you're going through and doing some practice problems. So anyway, paraboloid. Our traces, we have an ellipse that's parallel to the xy plane, right? And the paraboloid, and the other trace is a parabola that's parallel to all of the other planes. So if I have my x, y, and z axis, right? Essentially, I'm going to have these ellipses coming up, getting larger as I go up. And what we'll notice is that they will make kind of a parabola outline. So it's kind of like if I took a parabola and I spun it around and around, and that resulted in a three-dimensional shape. So we end up with this shape for our paraboloid. So it's not quite a cone. It's almost like a cone, but with a smooth bottom. And then lastly, we have our hyperbolic paraboloids, which is another one where we only have two of the variables squared. Difference though between elliptic and hyperbolic is the fact that one of them, both squared terms are the same sign. The other one, the squared terms are opposite signs. And for this one, we actually have hyperbola parallel to the xy plane, and then parabola um, parallel to all the others. So you know how we made ellipses going up the z-axis? This time we're actually going to make hyperbolas going up the z-axis. So remember your hyperbola looks like this. So that's that one. We could also have something that's not in the xy plane, but parallel to it. It's going to have our same dimensions here. And this would keep happening all the way up the x-axis. And there we go. It's like we have a little double taco shell thing going on. Taco Tuesday. All right, so with these quadric surfaces, key things, look at how many squared terms you have. If it's only two, paraboloid. Else, look further. Look at the squared terms. Are they all the same sign? If they are, ellipsoid. If they're not, then it could be a hyperboloid or a cone. Or if you've already determined paraboloid, that tells you whether it's elliptic or hyperbolic. Then look at the right-hand side of the equation. If it's equal to 1, right, then you have a hyperboloid if the signs were different. You have an ellipsoid if the sides were the same. You have a cone if the right side's equal to 0, and you have one side or one variable that's negative. Right, so that's kind of a short way for you to tell the difference between all of these different quadric surfaces. So now let's look at this in practice with a couple examples. So the first one, we want to classify and sketch the surface defined by this equation. So first, we have to make sure that we get everything in standard form, meaning I want to move my constant term to the other side. All right. And then I want to divide by the largest coefficient. What this does is it makes it so that we have x squared over a number, y squared over a number, z squared over a number. So I would have to divide all of these by 12. So I'd get x squared over 3 minus y squared over 4, right? Because 4 over 12 reduces to 1/3, 3 over 12 reduces to 1/4. And then plus z squared over 1, which I can just write as z squared, equals -1. Still not quite in standard form because I need this to be a positive 1 to be able to classify the type of, what's it called, surface. So I'm going to divide everything by -1. So I end up getting negative x squared over 3 plus y squared over 4 minus z squared equal to +1. Okay. So now let's look at this. All three variables are squared. That means it cannot be a paraboloid. Right? In addition to that, we have equals 1, so I know it's not the cone thing. I have two signs that are different, or two signs that are negative, one that's positive. That means that this is going to be a hyperboloid with two sheets. So hyperboloid of two sheets. And if I want to sketch this, all right, keep in mind which one is positive here, right? The y. So the axis that we're going to get our little two ghost cup thingies on is going to be along the y-axis. So if I draw my axes, we've got x, we've got y, we've got z. I know that, yeah, I know that we're going to end up getting this kind of shape. Okay. So that's our hyperboloid of two sheets. For the next one, yeah, battery. Okay, for the next one, we want to kind of look at this. First thing, how many squared variables are there? Only two. That means this has to be a paraboloid. So I'm going to rearrange it so that my non-squared one is on one side and everything else is on the other side. Now look at these two squared variables. Do they have the same sign or do they have opposite signs? They have the same sign, which means that this is going to be this is going to be an elliptical paraboloid. All right, remember it would be hyperbolic if they have opposite sides. Okay, and because x is the variable that's not squared, we know that the paraboloid is going to move along the x-axis. So we've got y, we've got z, we've got x. So our paraboloid is going to look something like this. And there we go. Last one. Classify and sketch the surface defined by that monstrosity. Well, this is going to be one of those where we have to actually complete the square. Mhm. Yep. So what I'm going to do first is I'm going to group anything that's an x with x. Anything that's a y with y. And anything that's a z with z. And I'm going to subtract the constant from both sides. Next, let's do variable by variable. So for x, look at my middle term, my coefficient for just x. It's -4. The rule here is you half it, you square it, you add it to both sides. So if I half -4, that gives me -2. Square that, I get +4. Now I have to add it to both sides. So thing about completing the square is that because we chose this constant to add, we know that this automatically is going to factor to x plus whatever half of this coefficient is, so x -2 squared. And if you were to expand that, you should get x squared minus 4x plus 4. With the y's, we actually need to factor this 2 out first before we can complete the square. Oh, whoops, that'll be 2y. And let me go ahead and complete the square for the z first. So look at your coefficient for z. It's -2. Half of that, -1. Squared, +1. Add to both sides. And we know that that's automatically going to factor to z plus half of the coefficient, so z -1 squared. Then on this side, if I add everything together, -3 plus 4, we get 1. Add 1, we get 2. Okay, and then the last part, we have to complete our square for y. Well, next to last part. So for this one, coefficient for y is 2. Half of that is 1, squared is 1. So I'm adding 1. Keep in mind, though, I'm adding 1 in the parentheses. So when I distribute that 2, I'm technically adding 2 to the left side of the equation. So because of that, I have to add 2 to the other side, not 1. Right? So whatever your thing is times this thing, that's how you get that number, this coefficient. Yeah. So we end up with x -2 squared plus 2 times y plus 1 squared plus z -1 squared equal to 4. Now I have to divide by the largest of these coefficients. So I end up with x -2 over 2 plus y plus 1 squared over 1 plus z -1 squared over 2 equals 4 divided by 2, which is 1, or which is 2. Also, to get this in standard form, I need this side to be 1. So we're going to divide everything again by 2. So 2 divided by 2, I get 1. There's already a 2 here, so this will become 4, 2, and 1. Okay, so at this point we have 3 squared variables. They're all the same sign, and we're equal to 1. That tells me that this is an ellipsoid. And the thing about this ellipsoid is that it's not actually centered at the origin. It's centered at the point 2, -1, 1. So on my XY plane, or on my three-dimensional plane, Y, X, Z, we're actually going to go, oops, there we go. Okay, we're actually going to go over positive 2 on the x-axis, -2 on the y-axis, and then 1 on the z-axis. Or not -2, -1 on the y-axis. So the center of this ellipsoid ends up being somewhere around there, right? So there, and then up 1. If I draw my ellipsoid, remember these numbers tell me my radii for each one, right? So for x and z, we're going to have a radius of 2. So x will bring you all the way back to the yz plane. And z will go up 2 as well. So we kind of have a circle in this way, and then a radius of square root of 2 in the y direction. So I end up with this ellipsoid that looks like that. And I will say before I leave that the most important part here is being able to rearrange these equations and identify what kind of graph it is. Because I'm not going to ask you to draw these graphs on a test, mainly because art would really get in the way there. All right, but it is important for you to be able to classify them and do the algebra to manipulate them, right? So with that, we are done with 11.6. Congratulations. Happy mathing.